happened. I haven't done anything yet. So, my name is Brian Brazel, and I'm going to talk about evolving Prometheus for the cloud-native world. So, if you don't already know me, I'm one of the main developers on Prometheus. I studied in Trinity, worked at Google for a while. I've contributed to many open source projects, and I'm also the founder of Robust Perception, which is trying to do the consulting and support chain for Prometheus. But enough about me. What am I actually going to talk about today, right? So firstly, I'd like to talk about how we got to where we are in terms of monitoring. Then I'd actually like to talk a little about Prometheus, because apparently I know things about it. And then looking at how Prometheus has changed over time as the cloud-native environment has evolved. There we go. Take this hand. So, if you look at a lot of monitoring and what's going on, and a lot of attitudes to monitoring we have today, a lot of it is based on tools and techniques from like the 90s and 2000s that were awesome at the time. Like I remember my first MRTG graph, getting it working after like an hour or two, and I was like, yes, I can see my CPU usage and my network usage, it's amazing. And it was. And we're also in a situation as well where we had not that many machines and not that many services, and they were lovingly cared for by sysadmins who, treated them kind of like their own children. And it's what we call pets these days. And special cases were the norm, right? Every service was special. Every service was a special case, being special love, care, and attention. And they have tools like Nagios in this world where machines are pets, and the services lived on one machine. We had the MySQL machine, the Apache machine, the Mail machine, right? One machine, one purpose. And there's always a situation where if any one of those machines deviated somehow, humans would jump on it, right? And fix it and investigate it, and we're going to make sure it's absolutely perfect. Lots of loving and care. But this also means that all of this heroism and this great attention to detail was basically also known as burnout. Because you're jumping on all these things with not much actual practical effect, that's basically feeding the systems with human blood. Not literally, usually. RAM can be very sharp. But, burnout's bad. We want to avoid it. And as we move into a cloud-native environment, we need kind of a new perspective. There we go. Okay. Yes. So what's kind of different these days? So, well, it's no longer the case that we have one service on one machine, and that machine and service is going to be there until the machine finally dies after we've replaced everything several times. Instead, we're in a world with systems like Docker and Kubernetes where services are being dynamically assigned to machines. And those can be moved around on an hourly basis due to auto-scaling or new releases or anything else like that. We're also moving into a situation where we're going from monoliths, you might have a handful of monoliths, to we might have tens, or if you're really lucky, hundreds of microservices. And this means that not just do we have these more dynamic services, but we've got far more of them. So the overall result of this, we've got a much more dynamic system, where things are churning and moving around a lot more, and there's much, much more to monitor. So that's kind of different, kind of more difficult. So we've got this setting. So let's talk about what Prometheus is. So Prometheus is a metrics-based monitoring system. Yeah, that answer never really satisfies anyone as to what it is. But it is what it is about. And there's a lot of people, talking some of the previous talks you saw, talking about tracing, talking about logging, and so on. Which are all useful techniques and important and complementary techniques. You need all of them. But the important thing about Prometheus is it doesn't care about every single request that comes in. Right? If you have 100 requests in the last minute, Prometheus is not going to remember every single one of those. But it is going to remember statistics which are kind of aggregated across time for those. So it's going to remember, hey, there were 100 requests. In total, they took 2 seconds. And 4 of them hit the cache, 3 of them hit that weird code path, and 1 of them resulted in an error. So it kind of has that overall view of all the different subsystems they took, how long they took, and you instrument it. And as well, Prometheus has a time series database at its core. A time series database just means a database that has time as the dimension. So this does, describe quite a lot of different systems with very different characteristics. But, Prometheus is one of those as well. Prometheus also has a pretty powerful data model. So if you're used to graphite, you have like the dotted string things where you have to know the position of, okay, that's the name of my data center, that's the name of my application, that's the name of my region, and that's Deborah. In Prometheus instead, it's key value pairs with arbitrary positions. No one pairs are unordered. So you can then aggregate by those by any way you want. If you want to aggregate by development, you can. If you want to aggregate by Europe, you can. If you want to aggregate by, actually, I don't care about any of the divisions. Tell me everything with the same binary, because I think something weird's going on with that binary. You can do all that. Another handy thing about Prometheus is the values are not integers, they're doubles. Now, this isn't that different. Hey, I've got a 64-bit double versus a 64-bit integer. What's the difference? The difference is, think about latency. If you're doing integers, what units are you going to use? Are you going to use seconds, milliseconds, microseconds, nanoseconds? And it turns out that people choose all of these depending on their personal context. And then never put the unit name in the metric name. So all I have is latency. Okay, look at that. It looks kind of like milliseconds. Hope it's not seconds, because we're in real trouble if it is. Hours, and in case you're wondering, this is theoretical. At one point, Prometheus was using all 4 of those units on the same slash metrics. Yeah, we're down to 2 now. We've only got microseconds and seconds. So instead, Prometheus, we just say because we've got floating point numbers, it doesn't matter because, it'll be taken care of by floating points, so we just have everything as seconds, so that problem kind of goes away. As well, you can do all the math you want there on those values. You can multiply, add, aggregate. You can join 2 different time series together, and you can use that. You can take quantiles. You can do predictions, using linear predictions, because when it comes to like hard disks filling up, static thresholds, either in percentage or in just gigabytes, don't work. However, linear regression is better. It's not perfect, but it's better. And an important thing as well is that you can use all these in graphs, but anything you can graph, you can alert on. There is no division between graphing and alerting. Just kind of handy. And in fact, these are the Wi-Fi metrics for FOSDEM, which has been using Prometheus now for 3 years. Not to know. And it's a snapshot from earlier, because unfortunately the Wi-Fi is not working in here last I checked. But this is all actually SNMP metrics for that we have in Prometheus. And Prometheus supports SNMP because I wanted to monitor my home switch. That turned out to be a lovely act shaving, but hey, pretty graphs. So another aspect of Prometheus is that reliability. If you look at a lot of systems in there, they're like clustered, they're complicated. It's very difficult to get that stuff right. Prometheus, the core of it is a single binary, a single Go binary statically linked. And each Prometheus server is independent. All it needs is a local SSD. You can also do a hard disk. It usually works. And let's say people will go ask, well, it's a single server. What happens, when they can't talk to something else for a while? Isn't there going to be a gap? And the answer is yes, there will be a gap. It happens, deal with it. Now this might seem a bit callous, but it turns out this is one of those things as well that's actually very difficult to get right. So let's say that either Prometheus or your service got overloaded, and that's the reason why it was failing its scrapes. You can pull the data. And let's say everything, the straw is removed from the camel's back, and we start getting metrics again. And it's like, right, let's backfill. So suddenly we're going to double the load at least, getting all that old data back in, and we're going to take out one of the services again. So you just caused the outage that you're trying to stop. So backfilling is something you need to be very cautious with, because it can cause outages because you're just increasing load in the service that's potentially just about to overload. So a simpler approach is, blips are going to happen anyway because of network weirdness, and you just get CPU timings wrong. If one happens every few hours, who cares? And we just build things to be more reliable because failure happens. Failure is normal. Of course, because Prometheus is based on a single machine, you're kind of limited to the disk space of a single machine. So for longer-term storage, you do want some form of cluster storage system. So you've got something called remote storage, which can send the data out and transparently read it back in. This is not reliable. So then we come to the more cloud environments, right? So if we have dynamic environments where it's not the case that ordering a new machine takes 6 months and a whole stack of paper, but instead that they can just appear as if by magic. because there's sufficiently advanced technology, you need to be able to check those automatically. You can't rely on a human pushing out Ansible or Chef or whatnot. So Prometheus has something called service discovery, which can talk to Kubernetes or EC2 or GCE or console and just get all the machines and continues to keep that updated. So as there's new application rollouts, as there's auto-scaling, as even new applications are added, it can automatically pick those up and start learning on them, as if you configure it. And even better, like Prometheus is a pull-based system, that means that because we've got a list of, from EC2 of here's all the instances that exist, if we, don't have information, we just try to scrape it, and it fails, we know, oh, it's down. With a push-based system, we won't be able to tell the difference between a system that was down and never talked to us, and a system that simply doesn't exist. So it's kind of handy, because you will find that if you do have like bottom-up systems that are telling you, oh, I exist, after a while, Crux builds up of instances that are there that aren't talking to you anymore, but you're still paying for. So you always do want some form of reconciliation to detect those. So that's kind of handy. Another thing to keep in mind is heterogeneity. Hopefully I will pronounce and spell that correctly. So normally, if you have services on like 5-10 machines, the chances are the machines are identical, like reasonably identical. But if you suddenly have tens of microservices with tens of replicas spread across like 100 machines, those aren't so homogeneous anymore. Because sure, it's the same instance type that you bought from Amazon or from Google or from Microsoft, but actually they have different CPUs with very different processing power and very different performance characteristics. And as well as that, who else is sharing that virtual machine with you might be polluting your cache lines or something like that, that's going to, make some of your instances slow. And if you've got, all these instances spread around the place for your service, let's say you've got 100 replicas for your service, and a few of them are slow, you can't be alerted on the individual instance being slow, because that's going to happen all the time, and that's not a good use of your time, because it's going to be paged continuously. And that's just going to, wake you up in the middle of the night, just like, oh, that again. But it doesn't matter, really, because it's not affecting the end user. As Tom was saying in his red talk there, we should be looking at what affects the end user and your SLAs. So we don't care about the individual instance being slow. We care about, is the overall user experience across all instances, is it all right? Is the overall latency okay? Is the overall error rate okay? And PromQL allows you to aggregate across that. So instead of alerting on, this one's a bit slow, and waking everyone up and saying, actually, the whole services within SLA are okay, the dodgy instance we can deal with in the morning. After you've had your tea/coffee in the morning. And this brings me to a more general point, that we're in environments now which are far more complicated than any one human mind can handle. We've got far more moving parts, we've got all these network overlays, we've got the kernel is getting more and more complicated, the applications are more complicated, we've got all these middlewares. There's so many moving parts, and they're changing so much over time, that alerting in everything that might pose a problem is just not practical. You can't do it, it's a Cynthian task. Even trying to enumerate and list everything, that can go wrong, not going to work. So instead, you do need, instead of looking at things that could cause things to go wrong, look at your symptoms, look at what your user sees, which is latency and error rate, or whatever the equivalents are for your systems. And then, as actually Tom showed quite nicely, you can drill down to your service based on your error rates and your latency, figure out, oh, it's this service here, and then within its subsystems, this is what the problem is, and then you pull out your tracing, you pull out your profiling, you pull out your logs. So that's kind of an overview of some of the things Prometheus is doing and can do to help you to deal with the cloud-native world and all its dynamism and all its churn. But Prometheus wasn't always, this good at it. It started off pretty basically, like was it 4 years ago now? It had very little in the way of service discovery. PromQL was not what it was today. And naturally, over these years, things have evolved. Prometheus 2.0, for example, which came out there a few months ago, brought improvements in two major areas. The big one was the new time series database, which is far more efficient. And also the new staleness handling, which I worked on, which better supports instances going away. Because, well, in an all static environment, machines don't go away that often. Maybe one every few months. You're in EC2 or whatnot, that can happen a few times a minute. So you need to be a little more careful, and the artifacts that cause are actually a problem. So, version 1 of Prometheus, or the V1 storage. So at the start of its life, Prometheus, like the first 2 years or so, everything was in level DB. All the actual time series data and all the metadata. So the metadata, I mean the labels, the multi-dimensional key-value pairs, identifying the series, because we need to like index them to say, hey, give me all node exporter things for CPU. And then we need to find all those metrics and pull them in. So it's a two-step phase. Look up your index, then pull your data. All of that's stored in LDB. If Prometheus was shut down or killed, you're going to lose 15 minutes of data, potentially. In terms of performance, it topped out at around 50,000 samples per second, which was still, shall we say, competitive within the space at that time. You know, that's quite a lot of samples. To just give you a context, if you had 500 machines that you were scraping every 10 seconds with 1,000 metrics each, that could deal with that. So that worked pretty nicely, even on like a reasonably large system. And I'm going to digress as to why you can't use MySQL for metrics, at least not this sort of volume. Because the problem you have is, if I'm pulling data from the machine or your Cassandra or whatnot, I'm getting like 1,000 metrics at this time with different names. But when I want to do a read, I don't want those 1,000 ones that I happened to scrape 2 hours ago. What I want is this one metric that was a part of 100 scrapes across time. So we've got a situation where everything I'm writing is the most recent value, whereas you're reading kind of horizontal. So what you end up having to do is you want to lay out the data so it's efficient to read and all the given metrics is together on disk. So that means you basically need to buffer up your writes a lot. And basically writing a time series database for these metrics basically turns out into having lots and lots of write buffering. And that brings us to version 2 of the storage engine, which is also in Prometheus 1, I point out. So this was part of Prometheus 09, which we launched just about 3 years ago, and this was written by Bjorn in Berlin. And it moved the time series data to a file per time series, which means, well, the data is all going to be together on disk. And then the writes were spread over 6 hours, rather than being flushed every 15 minutes or so. There was also double delta in compression, so we went down from potentially like 16 bytes per sample down to 3.3 bytes per sample. Because in principle, you'd have 8 bytes for the data, 8 bytes for the sample, so timestamp. And with regular checkpoints in memory state. So losing 15 minutes of data, no longer a problem. And over time as well, because we had this database for a few years, lots of other things were improved. We added some extremely basic heuristics to the indexing. Facebook released a Gorilla paper with an even better algorithm for compression, so we adopted that and we got like 1.3 bytes per sample, which is pretty good. There were some memory optimizations that were done. So, like last year, I was trying to do benchmarks on Prometheus to be able to tell people this is how much CPU and how much RAM you need. And trying to understand it, instead I cut resource usage by 30%. So, you win some, you lose some. But no one's complaining about resource savings. As well as that, one of the nice things Bjorn did, we made it easier to configure memory usage. Because if any of you work with databases, you know how there's like the 5 or 10 or 20 knobs you need to tune and try and guess how much memory usage is going to be. Prometheus had like 5 at this point, I think. Bjorn made it so he just said, here's how much RAM I want to use for the heap. And it would just adjust things and evict things to make that happen. Which mostly worked, and it made administration far easier. It's always good. So the outcome of V2 was far more performant. So the V1 storage engine, it was doing 50,000 samples per second. The V2 storage engine, the record of ingestion is about 800,000 samples per second. So that's a nice little boost. That's, what's that, 16x more performant? Or something like that. Yeah, 16x. But it wasn't perfect. Because if you want a Prometheus that big, it's not what you would describe as healthy. Because, well, it takes 40 to 50 minutes to checkpoint the data. And previously in V1, it was taking, 15 minutes. So this is even more data loss potentially. Now, this was all fine back when we were at the 50,000 samples per second, where your checkpoint was still taking 30 seconds. But as it gets larger and larger and larger, that became a bit of a problem. Churn, which is to say new time series, new targets, new machines appearing and disappearing, that affects the indexing. So the indexing, there's a practical limit of somewhere around 10 million time series within the database. Some people hit it at 5 million, other people pushed it to 20, 30, 40. but you're going to run into problems somewhere around the 10 million mark. And that's across the entire retention period. So if you've got a Prometheus which you've set to keep data for 3 months, and you're keeping on churning instances to releases and so on, you can burn through that pretty fast. As well, we've got a file per time series. So if you want to delete the oldest 10%, you have to rewrite the entire file, because only XFS supports truncation of files, and well, we can't presume that exists. So that's a 10x write amplification factor, and it is known Prometheus, this version of it, killed SSDs on several locations. Yeah, like when Johannes Fish first ran on the Raspberry Pi, it killed the SSD. It wasn't too surprising as it was compact flash. But when also more production stuff was also being hit by write amplification, not the best. As well, LevelDB is using Seagull implementation, and we did get to the point in Prometheus where we started discovering issues like file system bugs, kernel bugs, and bad hardware. So we are at the issue where we're starting to see weird stuff. But we're seeing corruption and crashes, which we tinker inside LevelDB, but we can't really debug them because it's C code, and we can't really debug them from Go. So it's not perfect. So where can we go from here? Because we want something that ideally will be dealing with high churn, that's more efficient at all this label indexing, so we don't have this 10 million limit, and avoids write amplification. It'll also be kind of nice to be able to take backups, because some users want to do that, because if you have a Prometheus that's realistically taking 20 minutes to do a checkpoint, that means it has a 20-minute shutdown time. Then you take your snapshot, then you turn your Prometheus back on. Regularly taking your Prometheus out for 20 minutes is probably not what you want to be doing for backups. You can tolerate 5 minutes once a week or once a month, but 20 minutes a day, not likely to cut it. So this brings us to version 3 storage, which is in Prometheus 2.0, and this was written by Fabian. And the principle is that is instead split into blocks, which are 2 hours long initially. You build up the blocks in memory, and you write them out every 2 hours. There's also compaction later on to put them together. There's inverted indexes with posting lists, so nice modern approach. And everything is accessed by an mmap. So previously Prometheus was already doing its own memory management. Now we just let the kernel take care of that in page cache. So we're now in a situation where Prometheus just uses as much memory as it needs, so there's no longer any configuration required. And there's also a write-ahead log for crashes and restarts, so a restart will, in the worst case, take about a minute, which is pretty sweet. So the outcome is, we're still in the early days yet, we're starting to get people onto it, but millions of samples ingested per second is certainly possible. And if you look at other similar systems, not just time series databases, but other databases, and see how much performance they can get from a single machine, the numbers top out somewhere around the 1 million to 4 million samples a second range. So it does seem that we're getting pretty close to the theoretical maximum of what you can actually get out of a single machine, which is nice to know. The read performance also improved quite a lot due to the inverted indexes, though some things have slowed down a little bit. And memory and CPU usage were down about a factor of 3 due to heavy micro-optimization. It's been optimized to hell and back, basically. And disk writes, because, well, we're no longer writing all these files, basically IOPS are down by a factor of 100, which lots of people thank us for, which is good. So let's just look then at what Prometheus and Prometheus 2.0 now has, because it is based on years of monitoring experience. And the new time series database is far more able than the previous systems to deal with these highly dynamic environments. So Prometheus has grown as easy as it grows. Service discovery, it knows what to monitor. PromQL allows alerting on the things you actually care about, rather than the things you can alert on. So you don't have to alert on the CPU usage being high, you can actually alert on latency is high, which is probably what you actually cared about. And this means that Prometheus is a pretty good choice for the cloud-native metrics monitoring, because it has a community as well of thousands of companies using it. There are hundreds of exporters. There's 15 different client libraries, at least 15 different languages for client libraries you can write your own instrumentation for. It is a big community, and it is only growing. And also, I have to announce that there is a book that I am presently writing, which will hopefully be out in a few months, and no news yet on a stage play or action figures. And will evolve. So at that point, I would like to invite you to stay so people can ask questions. There's about 10 minutes, I think, 8 minutes.
Okay, question?
You said that it uses compaction. Compaction is normally in by write application. How do you avoid that?
So the question is that I said we're using compactions, and this implies great amplification. So how do we avoid that? It's like, yeah, you're right. So it's not as bad as previously. So I think it will normally only write it like 2 or 3 times rather than 10 times. Works out in total. I'd have to check the exact numbers. More questions for Fabio. Next question.
Who would play you in the film?
So Tom's asking who played me in the film. I don't know, if you grew your hair out, you might be able to do mine.
They took off the foot off my film.
Hey Brian, can you talk a bit about how work on Prometheus is funded and what's next on your roadmap?
Okay, so the question is about funding for Prometheus and roadmap. So Prometheus is a pure community project. There is no one company behind it. So how is work funded? So for example, my company, we're going to support the consulting route for Prometheus. So you can give us money for a support contract, and I will hire more and more developers to work on Prometheus. There are other companies like CoreOS, now Red Hat, who, they have a product that includes Prometheus for their monitoring because they have a cloud thing that needs monitoring. Prometheus looks good. They're putting developers on that. Even before that as well, Red Hat was putting developers on it. SoundCloud still has some developers. GitLab is also integrating Prometheus into their product in some pretty cool ways. So they're hiring developers, although they're also working with internal tools, plus a few other people with project have been around. But the answer is largely the same as most open source projects, which is it's coming from corporate interests, whether they're using Prometheus internally and want to expand it, or they're providing support services and this is the way to kind of advertise. In relation to the roadmap, I'm not sure, there's talks about improving the UI and doing the rewrite. We obviously want to make things more polished, expand things, maybe add TLS to the various endpoints once we have the actual people resources to be able to do that, because it is a bottleneck of how many people we have, especially with the growing community. Next question.
With Prometheus being developed to capture the state of the system or in the network in the here and now, and this usually applies for services and systems, etc. What's the weirdest thing you've ever heard being monitored or tracked by Prometheus?
So what's the weirdest thing I've heard being tracked with Prometheus? Satellites. So it turns out there's this company, it's not SpaceNet, which is British, something like that, who basically have satellites in orbit, which are like 2U size, that take photos, and they're tracking actual telemetry with Prometheus, of satellites. And I think there's the node exporter possibly running those as well. We also know that Deutsche Bahn is running the node exporter on all their platform signaling things, plus various home uses. Of course, someone's done Bitcoin, someone's done their local petrol prices, temperature is being done, environmental data is being done. People are doing everything with it. Yep, next question.
Okay. Could you tell us a little bit more about this time series database that is being used in the newest version? Is this something being developed from scratch? Some leveraging on some time series databases already out there?
So the question is talk more about the time series database within Prometheus. Okay. So if you look at systems and how databases are designed, there's only so many models for doing it. So we're using similar design, for example, to also InfluxDB's B3 design, suspiciously similar because there's basically only 1 or 2 designs for these. So you've got your 2-hour block. Prometheus is just getting in all the data, assembling it all, chunking it up in memory, doing all that buffering you need, and writing it out. So when the query is needed, Prometheus has all these blocks on this. So firstly, it goes to each blocks, which has its own index, saying, right, do you know that the node export is CPU usage? And going for each of those, and then assembling that all together. And then that data is continuously written to. There's a head block, which is entirely in memory, and then that's all feeding down through. So it's a pretty typical database design. Fabio has a good talk. Was it storing 16 bytes at scale from the last PromQL, which will probably give you the most detail on that.
Okay, time's up. Thank you very much, Brian.